Hello everyone, today we are here for the Stratos jump by Felix Baumgartner. The goal of this video is to investigate Felix's jump, analyze and calculate the video at various points. We'll also investigate the effect of air resistance on the daredevil's velocity. We'll also go over Newton's second law, first and second law, time-related graphs, analyze real-time data to analyze the motion, and go over errors and assumptions. Newton's first law states that a body in rest or uniform motion will remain in that thing until and unless there is an external force applied on it. This is also called the momentum principle. Newton's second law states that the dp by dt is equal to the force both in magnitude and in direction. Initial condition is that the height is 39,000 meters, t is 262 seconds. This is before deploying the parachute. G is 9.8 meters per second squared. Please have a look at this video. This is a long video though. This is the equation of net force. This is how I get it. Though I'll go over this when we are doing the computation modeling. So when the skydiver steps out of the capsule and into the void, he will accelerate for 30 seconds before reaching his top speed, and then the air resistance will oppose the downward motion, counteracting the downward force of gravity pushing it. So basically, what happens is when the skydiver jumps down, at 39 kilometers up from the ground, the density of air is very less. But as soon as the skydiver jumps and starts coming down, the density of air increases, which means that the daredevil will face more and more drag, which will lead to a decrease in velocity after 30 seconds. This is the P which is used to model the air density, and this is why as we come down, the drag increases, decreasing the velocity of the daredevil. And in this part, the mass of the daredevil is 110 kgs. Obviously the acceleration due to gravity is 9.8, and then the air resistance for my model, I modeled it to 0.0078. It is very less. We'll just see that. The F drag is obviously B, which is the drag constant into magnitude of the daredevil's velocity. The force of gravity is just mg, and this is how we get F net. The graphs look something like this, though I've tried to use the model of a very fast moving thing and to show that the air drag I have used constant does not really work that well. This is the real-time data analysis. So you can see as soon as he reaches around like 30-40 seconds, it's like 1340 kilometers per hour, which is a lot. And as soon as the 260 seconds come, the velocity drastically decreases. This is the real-time height versus time graph. So the slope indicates the speed, and as you can see, first the slope is very steep, which means he's decreasing a lot. But as he comes down, the density increases, so does the drag, and we see a gradual decline in velocity to the point where it decreases a lot. Then as soon as he deploys the parachute, there is a stark decrease in velocity. This is the velocity time graph. As you can see, until the time there was very less drag, Felix kept on accelerating very fast. But as soon as the drag increased, it was the decline started. There was a rapid decline, and this almost steep graph shows around the time when he deployed the parachute. Q&A: how high Felix should be if he wants to break the sound barrier? It's 46 seconds. What effect does a change in density of air, the altitude, have to do with our prediction? As the altitude decreases, the density of air increases, as the drag increases. What effect does the change in temperature with the altitude have on the predictions? Temperature increases as the altitude decreases. How long could he wait before he had to open the parachute? It's 262 seconds. Obviously, there were many errors in the modeling I showed previously. We had assumed that the daredevil's fall is perfectly straight. Well, obviously it was not. We neglected various airstreams. The distance calculated by the using the video, there could be some inconsistencies in the measurement. The peak velocity was at 46 second mark, which was 282 meters per second. The effect of drag played a key role in decreasing the velocity of the daredevil and saving the life. Thank you so much for watching the video. Have a nice day.